Hi, welcome to our Pharma Topics channel. Welcome to the 36th series, part B of quantitative structure activity relationship. In previous video, we have seen the basics of QSAR. In this, we will be discussing about the statistical methods, the 3D QSAR, CoMFA and COMSIA. Let us see the statistical methods involved in QSAR modeling. One is a method of least square fit, that is R square, cross validation, that is Q square, adjusted R square, that is R2 adjusted, chi-square test, and root mean squared error, bootstrapping, scrambling, that is called Y randomization. First one is least square fitting, that is called R square. Least square fitting is the most commonly used validation method and applies linear regression analysis. It measures the square correction coefficient, that is R square, between the predicted and the experimental value of the activity. To optimize QSAR model, the outliers can be removed from the training data set, and the best model should have a difference of the R square and R square adjusted should be, that is R square minus R square adjusted should be less than 0.3. Next is internal validation by chi-square and root mean squared error. The chi-squared and RMSE values are used to measure the predictive quality of a model generated. Chi-square value displays the difference between experimentally determined biological values, that is IC50, EC50, K, Km, and so on, and the values predicted by the model. In contrast, RMSE value depicts an error between the mean of the experimental and the predicted activity values. The models must possess a large R square value, that is greater than 0.7. Chi-square value and RMSE should be lower, that is chi-square should be lower than 0.5 and RMSE should be lower than 0.3 for good predictive ability of the model. Next one is cross validation, that is Q square. Q square cross validation repeats the regression many times on the subset of data. There are some concepts like leave one out, that is LOO. One compound is randomly omitted in this approach and the QSAR model is constructed using remaining set of compounds. Suppose you have 100 compounds, one compound becomes the training set and others become the test set. Then the second compound becomes the training compound and the other compound becomes the training set. Like that it goes on. There are many iterative steps which are involved. It undergoes iterative rounds to construct the best model. It is a very older model. Nowadays it is not followed. Next is leave some out. More than one molecule is left out at a time, and R is computed using predictive values of missing molecule. Leave many out, more than one molecule is left out at a time, and R is computed using predictive values of the missing molecules. It is larger than the LSO, that is called LMO. It's a measure of goodness of prediction. For good predictability, R square minus Q square should not exceed 0.3. Next is the predictability of the model is further assessed by PRESS, that is predicted residual sum of squares, and cross validated R square Q square when standard deviation error of the prediction is obtained from PRESS. So it appears like this. The PRESS will appear like y. It is the sum of the y observed and y predicted, the whole square. Then cross validation, it is Q square. It is 1 minus y predicted and observed square by 1 observed minus mean, the whole square. This is the cross validation. Other parameters of internal validation are cross validation Q square. There is another formula for that. If you are able to remember this, you can use this formula 1 minus, which we have seen in the previous slide also. Then squared correlation coefficient, that is R square. Then there is one more thing called R square M. So this is R square into 1 minus square root of R square minus R naught square, where R square and R naught square are the squared correlation coefficient values between the observed and predicted activity data with and without intercept respectively. Models with values of the R, M, square metrics above the threshold value of 0.5 are considered to be good predictive ones. So R square M should be greater than 0.5. Next is bootstrapping. It is another approach to internal validation alternative to the LMO. Simulating data sets are generated from larger data sets. Statistical analysis is performed on each of the simulating data sets. The component model with the consistent results is chosen as the final model. Next is Y scrambling. Scrambling the data. Scrambling is how you break the egg. That is called scrambling. Scrambling the data in different permutations and randomization is another method to check the robustness of the QSAR model. It is used to identify models based on chance correlation. The dependent variable is randomly shuffled and a new QSAR model is developed using original independent variable matrix, calculating the quality of the model. The process is repeated several hundred times and the resulting model should have low R square and a low Q square. Next is external validation in QSAR. External validation is testing the predictive power of a QSAR model, comparing the predictive and observed activities of a large external test set of compounds that were not used in the model development. If R square predicted is more than 0.6, then the model is considered to be predictable. Outliers, it is defined as the structure with residual greater than 2 times the standard deviation. First one is there are many methods in QSAR. One is a regression analysis. It is a mathematical technique which correlates the dependent variable x with independent variables y. One is a simple linear regression. An independent correlates with a dependent variable and produces a linear one-term equation is called simple linear regression. It is useful for discovering some of the most important descriptors. Next is multiple linear regression. Multiple linear regression method predicts a correlation between independent and dependent variables. Biological activity or physicochemical properties are examples of dependent variables and molecular descriptors are independent variables. It is in simple linear regression models, dependent variable is predicted used only one descriptor or a feature. MLR models consider more than one descriptor for the prediction of property or activity in question. MLR is represented by the equation y equal to a plus bx. Y is the dependent variable representing the physicochemical property or biological activity. X is the independent or predictor variable accounting for molecular descriptors. B is the regression coefficient. The number of variables should be 1/5 of the molecules in the series. For every 5 molecules in the series, one can have one variable. The next method is GAMLR. Genetic algorithm based optimization methods are based on evolutionary principles. Each variable used in the calculation is considered as a gene. One included in a model, 0 if none is included in the strings of the bits. Inspired by the process of natural evolution, a chromosome, that is a strings of variables combined together. It is a p-dimensional vector where each position, that is a gene, corresponds to a variable. GA uses combination of two parent chromosomes, then using the genetic recombination approach to form new chromosomes that have better fitness. They provide efficient optimization to process the information quickly. First one is another method in QSAR is partial least square PLS. PLS is very suitable if hundreds or even thousands of independent variables. That is X block correlated with one or several dependent variables. That is Y block. X block is independent variables. Y block is dependent variables. PLS is used when X data containing collinearities. N is the number of compounds and M is the number of independent variables. PLS is a method of choice in 3D QSAR method such as comparative molecular field analysis, that is CoMFA. PLS is also used in validation metrics of the models. It is advantageous over the other regression models. PLS has been used in the construction of many successful QSAR models. The PLS identifies the relationship between two matrices X and Y, where X is the orthogonal latent variable derived from linear combination of the original variables obtained by principal component analysis. It is used in cases where the number of variables exceeds the number of observations. It follows a multivariate approach, beginning with a larger number of variables and extracting to a few principal components. PLS models are more difficult to understand and interpret, and MLR is more commonly used. QSAR guided drug discovery. So the QSAR guided drug discovery will be like this. It is an outline. So you will give the molecular descriptors, the lab data, or you may give literature data. The data is collected, curated, and integrated. Then you give the QSAR software. It predicts the QSAR workflow. A QSAR model is generated. You get a best fit model. One of the equation you select, and you do virtual screening and molecular design. Then you can reconfirm with the experimental validation, which can guide you for the drug lead molecule synthesis. Let us see the 3D QSAR. 3D QSAR refers to the application of force field calculations requiring three-dimensional structures at a given set of small molecules with known activities. That is the training set. The training set needs to be superimposed, that is aligned by either experimental data, that is based on the ligand protein crystallography, or molecular superimposition software. It uses computed potentials such as Lennard-Jones potential rather than experimental constants, and is concerned with the overall molecule rather than the single substituent. The first 3D QSAR was named Comparative Molecular Field Analysis, that is CoMFA, by Kramer et al., which is examined the steric fields, shape of the molecule, and the electrostatic fields, which were correlated by means of partial least square regression. The steps followed in QSAR. First step is the optimum or the near bioactive conformation of the compound must be determined either from X-ray crystal structure or NMR by experimental studies or a theoretical tool like molecular mechanics. The optimization of the energy has to be performed in this step. The next step is alignment of conformers in the dataset has to be generated in the 3D space. The third step is a stable conformer is probed computationally for generating various descriptors. Then finally, the computer descriptors should be correlated with the experimental biological activity. The assumptions in 3D QSAR. Binding of a drug molecule or a ligand with a receptor is considered directly related to the biological response. The effects of second messengers are not considered. Molecular properties such as physical, chemical, and biological are encoded with a set of numbers or descriptors. It is believed that compounds with common structures have comparable properties and they have similar binding modes and accordingly equivalent biological activities and vice versa. Structural properties leading to biological response are usually determined by non-bonding forces, mainly steric and electrostatic ones. Another critical assumption is that the biological response is showed by the ligand itself and not by the metabolic product. So this is not considered in the 3D QSAR. The lowest energy conformation of the ligand is its bioactive conformation, which exerts the binding effects. The geometry of the receptor binding site is considered rigid, though there are few exceptions. The laws of translational and rotational degrees of freedom, that is entropy, upon binding is believed to follow a similar pattern for all the compounds. The protein binding site is assumed to be same for all the studied ligands. The major factors which contribute to overall free binding energy like desolvation energy, temperature, diffusion, pH, salt concentration, and plasma protein binding are challenging to identify and generally ignored. Let us see the 3D QSAR workflow. So there will be around 8 stages in the 3D QSAR. In the stage 1, it is curation of chemical data set. Curation means it is removal of the inorganic compounds, structural modifications, treatment of tautomeric forms, then manual inspection, then analysis and removal of duplicates. That is a pre-preparation. then you get a curated data set. This data set in the step 2, it is a generation of descriptors. It may be from 2D, 3D, 4D, or depending upon your requirement, you can go for up to 6D descriptors, molecular descriptors. Then in the stage 3, you split the data into training set and test set. Then you build a QSAR model. Then you validate the QSAR model in step 5. Then in stage 6, virtually you can design the ligands. Then prediction and selection of best ligands is stage 7. And in the stage 8, experiments to validate these compounds, which confirms this model is a perfect model. Let us see the types of 3D QSAR techniques. There are three bases. One is based on the employed chemometric techniques. One is linear, where CoMFA, COMSIA, and SOMFA are used. Non-linear techniques use compass. Based on the alignment criterion, which is alignment dependent or CoMFA, COMSIA, CHARMM, AFMOC. Alignment independent or compass, comma, Walsurf. Based on the intermolecular modeling or information employed to develop QSAR. One is ligand based. You can use CoMFA, COMSIA, CHARMM, and receptor based means you can use AFMOC and HIFA. Let us see what is CoMFA. Kramer et al. Developed a comparative molecular field analysis, CoMFA, based on the molecular field alignment dependent and ligand based method, which helps in building QSAR. The ligands are placed in energy grid at a lattice point. The energy is calculated. The resultant energy is calculated at each unit fraction corresponds to electrostatic, that is Coulombic, and steric van der Waals properties. The computed values serve as descriptors and are then correlated with the biological responses employing a robust linear regression method like partial least squares. Let us see the factors influencing the quality of CoMFA. One is biological data. All the molecules should belong to a concentric series, possess same mode of action, or bind at the same time, and experimental data collected should be from a single laboratory. Optimization of the 3D structure of the ligands. Conversion of the ligand structures to 3D, followed by optimization with molecular mechanics, quantum mechanics, and semi-empirical methods like MNDO, PM3, AMI, etc. And conformational analysis of compounds. Systematic search, Monte Carlo method, molecular dynamics, simulated annealing, or by applying genetic algorithms. It's a very important question in CoMFA. CoMFA is a comparative molecular field analysis, which is very widely used in 3D QSAR. It was developed by Kramer. The methodology followed by CoMFA are ligand selection. The set of ligands has to be selected. The receptor has to be taken into account. The ligand has to be prepared. Bioactive conformations of each molecule has to be prepared. Then they should be aligned. All the molecules should be aligned. Then field calculation. They will calculate the field around all these molecules. Then a model is generated. Usually they go for multiple linear regression or partial least square, and that displays the results in a 3D space. So it will be like this. All the molecules are put in a grid space and they are superimposed, and they study the contribution of each substitution. So this approach is CoMFA approach. Let us see the alignment of molecules in CoMFA. The most commonly used methods are atom overlapping based superimposition, binding sites based superimposition, fields pseudofields based superimposition, pharmacophore based superimposition, multiple conformer based superimposition. So these are the alignment procedures which are used in CoMFA. Let us see the display and interpretation in CoMFA. So it will be like this. It will give a prediction for the experiment. One will be the training set, one will be the test set. So it will give a predicted IC50. A model will be created, and it will give plots called contour plots like this. See, the contour plots will be there for steric electronic features, hydrogen bond donors and hydrogen bond acceptors. Let us see the advantages of CoMFA. CoMFA considers physiochemical features like steric and electrostatic forces involved in ligand receptor interactions. This method is directly applicable to any series of molecules for alignable modes can be constructed. Alignment should relate biological activity. This method represents the entire ligand's interaction energy and not just the interaction of a more or less randomly selected substructure of the ligand. The contour maps representing the lattice needs only molecules as input with the with their lattice description and alignment. What are the limitations of CoMFA? Too many variables like overall orientation, lattice placement, step size, and probe atom type are considered. So it is a limitation for CoMFA. It's not suitable for in vivo data. There is a low signal to noise ratio due to many ineffectual field variables. There is improbability of choice of molecules and variables. Some potential energy functions are inconsistent. Hydrophobicity is not well quantified. So let us see what is CoMSIA, comparative molecular similarity index analysis. So what is the difference between CoMFA and CoMSIA? It is a comparative molecular field analysis, whereas this is a comparative molecular similarity indices analysis. The electrostatic and steric potential of ligand aligned molecules are taken into account, whereas here in CoMSIA, it is a Gaussian function of interaction energies. The Lennard-Jones potential and electrostatic potentials are characterized by Coulomb type and may cause deficiencies if they occur apart from a grid space. The deficiencies which arise out of Coulomb type are addressed by CoMSIA. Only grid space is considered and molecular similarity space is not considered in CoMFA. Molecular similarity space is considered in CoMSIA. Hydrophobic descriptor fields are not considered in CoMFA, whereas hydrophobic descriptor fields are well considered in the CoMSIA. Hydrogen bond donors and acceptor fields are not well considered in the CoMFA, whereas hydrogen bond donor and acceptor descriptor fields are considered in CoMSIA. Contour maps indicate the aligned molecules will interact favorably or unfavorably with the probe atom, whereas in CoMSIA, contour maps indicate steric, hydrophobic, hydrogen bond acceptor or donor regions which favor and disfavor. Let us see the CoMSIA model generation. It will be like this: drawing a set of molecular or chemical structures, then generation of conformers, followed by energy minimization of the molecules and the calculations of the partial atomic charges, then alignment of training set molecules based on the points of alignment of most of the active compound, then calculation of similarity indices as independent variables such as steric, electrostatic, hydrophobic, hydrogen bond donor and acceptor properties, uh, then interpretation in the form of colored contour plots in 3D space. Then generation of CoMSIA model by partial least square analysis, then followed by progressive scrambling to optimize the component number, and the activity could be predicted for the test set molecules which is externally validated. So this is a CoMSIA model generation. Let us see the CoMSIA interpretation. So like CoMFA, it also gives the predicted IC50 for the and the experimental PIC50. So the plots will appear like this. It is also very similar plot when compared to CoMFA, but the contour plots give additional information. Whether the increase or decrease is given by CoMSIA. It gives steric, electronic, hydrogen bond donors, hydrogen bond acceptors, because these regions they indicate that they increase. So the colored regions, it indicates this region is having, it is a favorable region. This is the outline of CoMSIA. The softwares used in QSAR, QSAR for you, then QSAR toolbox, and very famous QSAR ins for multiple linear regression models development and validation. You can use an Excel sheet also for QSAR model generation. Let us see the interpretation results of QSAR. I have given some of the examples how it will appear. Let us see a overfitted model. So here you can see the predicted as well as the experimental values, they overlap. The line overlaps. The green line overlaps the blue line. So this is a overfitted model because here two lines are appearing, but it appears as a single line. Then let us see a underfitted graph. So underfitted graph will appear like this. The molecules are scattered throughout. So here you can see several outliers are present here. So it is an underfitted graph. Then let us see a failure regression model. So there will not be a regression. The R square value will not be around 1. So it will, some molecules will only fall in. So this is a failed regression model. Then interpretation of results such as partial least square, cross validation and heat maps. So this is partial least square map. Then cross validation and heat maps are also used in QSAR. So it's a very short information of CoMFA COMSIA and 3D QSAR. I hope it will be useful for you. Thank you for listening. Happy learning. Kindly share this to more of your friends. Kindly subscribe to our Pharma Topics channel. If you like this video, kindly press the like button. Go through all the series of videos in the playlist of Pharma Topics, Principles of Drug Discovery, and score well in your exams. Thank you.